Hi, so welcome to lesson 3. We're going to go through confidence intervals and connect them to hypothesis tests that we have been doing. These are still focused on one sample confidence intervals, so it's either a one sample proportion or a one sample mean. For this lesson, our goal is to be able to create a confidence interval to estimate some population proportion or population mean. We want to be able to interpret what that confidence interval tells us and make decisions about a hypothesis test from a confidence interval. Lastly, we're going to describe what a type 1 or a type 2 error would look like in the context of our statistical scenario. So let's introduce this idea for a second. A sample of 400 North Carolinians found that 55% identify as a Carolina Panthers fan. Does this mean that exactly 55% of the state are fans? Or should we expect some wiggle room around that number? When we think about this, this is what one sample tells us. And if we took another sample of 400 North Carolinians, we probably would not get exactly 55% again. So why might a single number be misleading? A confidence interval helps allow us to get that wiggle room that we expect because we know that samples will vary, and that variation is important. We expect that, but we can also predict what that variation will look like. So a confidence interval is a range of values built from sample data that's likely to contain that true population parameter. We don't know what the true parameter is, that's why we're trying to estimate it, but we estimate it with a range of values. So instead of giving just a single estimate, like 55%, it provides a range of plausible values that account for this sampling variability. So why do we use them? We want to express that we are uncertain when we get a sample statistic. That sample statistic is likely not exactly equal to the population parameter. So instead, it helps give that range of plausible values. To help decide whether a hypothesized value, like 55%, is reasonable, we can check if this would fall inside the interval of plausible values. We also use them to provide more information than a hypothesis test alone. A hypothesis test will tell us to either reject or fail to reject our null hypothesis, but it doesn't tell me what we think the true parameter might be if we did reject the null. So we'll get back to that in a few more slides. When we do a confidence interval, it's tied to a confidence level. A 95% confidence level is often very common, but there are other levels as well. So we typically use a 90, 95, or 99% confidence level. That confidence level helps express what the probabilities are tied to, because this is looking at the likelihood of capturing the true parameter, and it's based off of our sampling distribution theory that we know. So a 95% confidence interval doesn't guarantee that the true value is inside this one interval, but if we repeated the process many, many times, about 95% of those intervals would capture the true parameter. So here we have a picture that shows several confidence intervals and the true population proportion mu. This is what our sampling distribution of x bar would look like, so our sample means. And we can build that sampling distribution based off of what we know of how samples are distributed. So with some theoretical knowledge, we were able to develop this idea of a confidence interval. We are focused on a confidence interval for a proportion or a confidence interval for a mean. We've done that in Excel in Math 152, but we're going to stray away from all the formulas that we learned and go straight into R and let R do the calculations for us. So we need to know what code we will use to run a confidence interval in R, but we first have to decide what type of test we need. We had a prop.test and a t.test function that we used earlier, and we're going to use those exact same codes for the confidence interval. In fact, we saw the confidence intervals show up in the previous lesson when we were doing the hypothesis test because they are connected in that code. So for the proportion confidence interval, prop.test, you see a few new functions inside that code. So we have an argument about conf.level. This confidence level is represented as a decimal. So a 95% confidence interval, we're going to type in as 0.95. And then notice I've also included another argument that says correct equals false. There's a continuity correction that's default that happens in this proportion test. So we just want to turn that off. We don't really need to know why that's happening right now. We just are trying to create the same confidence interval that we've seen before. And so we turn that off by doing correct equals false. For a t-test, we use the same command we did earlier, where we grab the specific variable that we're trying to run a confidence interval or hypothesis test on. That variable is our numeric data, and it needs to be defined in R. I'll show you how to do that again. That might be where you type in the data first, or you're importing the data into R. We specify what the confidence level is. We can change that to a 90%, a 99%, or whatever confidence level we need. For the means test, we do need the sample's raw data. So we can't have summary statistics and run a confidence interval like we did for a confidence interval with the formulas in Math 152. So that's one limitation that we're using here with R, because we're building this off of the raw data. There are ways that we could create that confidence interval based off of summary statistics, but we're not trying to learn all of those formulas and how to type them into R. We're focused just on using these two lines of code. The conditions for a confidence interval for a proportion are identical to a hypothesis test for a proportion, so we still need randomness to help our sample be representative and avoid bias. It needs to have the independence. Each observation should be independent of others. If we're sampling without if we're sampling without replacement, we check that 10% rule. And then the normality condition for a proportion was looking at having at least 10 expected successes and 10 expected failures. This is sometimes called the large counts condition. And 10 expected successes is really just a generic rule. Some textbooks might use a different number, but we're just looking to see we have a certain number of successes and a certain number of failures to approximate this sampling distribution out to be a normal distribution. The same conditions for a confidence interval for a mean are similar. We have, in fact, I need to change this one word here. We have randomness, independence, and normality again. This is normality condition for a mean, not a proportion. But we had the central limit theorem that said as long as our sample size is at least 30, then the sampling distribution of x bar will be approximately normally distributed. Now, if the population was already normal, then the sampling distribution will also be normal. But if we have a small sample size, we don't know that the sampling distribution will be normal, and we don't know that the population was already normal. So we kind of have to justify that off of the sample data we have. We check that with a histogram, a box plot, or a QQ plot, that normal probability plot. That confidence interval that we learned in Math 152, we talked about a formula, and it was based off of our point estimate and the margin of error. The larger our sample size, the more data we have to build this off of, so we end up with a narrower interval, but a smaller sample size would produce a wider interval. The more data we have, the more precision we have to be able to get and hone in on that parameter that we're estimating. When we look at the variability, that's also going to affect our confidence interval. If there's a higher variability in our data, we end up with a wider interval. So messy data would lead to a less precise estimate. However, if there's less variability, then we can get a narrower interval. Lastly, the confidence level also impacts the width of a confidence interval. A higher confidence level will lead to a wider interval, whereas a lower confidence level produces a narrower interval. We saw this example from the hypothesis test lesson. So this is about that campus health center that's evaluating its flu vaccination program. We had a previous year of 40% of the students reporting getting their flu shot. And then we looked at what's happening this year. That campus health center pulled some data and saw that in a random sample of 120 students, 58 received their flu shot. So now we're not looking at a hypothesis test, but instead we want to create a 95% confidence interval for the population proportion of all students who received a flu shot at the campus health center. We're going to use that same prop.test function, but we're going to add in our conf.level and correct equals false. 58 and 120 were the number of successes out of the total sample size. When we do this in R, it will produce similar output as to what we saw before, but now we're focused on the 95% confidence interval section. It gives us an interval that goes from a lower bound of 0.395 or 396 all the way to an upper bound of 0.572 if we round off. We want to create an interpretation from that. So this interpretation is likely the same one you saw in Math 152, but I would say something similar to: we are 95% confident that the true proportion of all students who received a flu shot from the campus health center is between 39.6% and 57.2%. The second example that we saw in the hypothesis test lesson was about how much sleep that students are getting on average per night. So we collected a sample of 20 students and recorded their average nightly sleep for the past week. Now we want to create a 95% confidence interval for the mean number of hours of sleep per night, and we use that t.test function in R. So we will type t.test and then grab the variable sleep, but I do need to define that variable first for R. And then the confidence level is 95%, so we do conf.level equals 95 or 0.95. We end up with this output where the confidence level goes from a lower bound of 6.35 all the way to 6.76. We would then interpret that to say we're 95% confident that the true mean number of hours of sleep per night is between 6.35 hours and 6.76 hours. And before I do example 3, let me back up and show what that looks like in R. So for this, I've already pre-typed some of this in, but again, I use the commented code of hashtag lesson 3 just to kind of organize the information here for this. This is in my script pane, or the source pane. I have this again in a different order than some people do, and that's okay. You can change the layout of your panes if you want by going to Tools and Global Options and then Pane Layout. You can adjust what you want in each corner. I also changed the appearance of my screen. So instead of it being default white, I changed it to this inverted black screen with colors instead. So prop.test here is the code that we used. When I want to run that line of code, I can highlight it or go to the end of that line and press Command Enter or Control Enter, and that will run that line of code. We see the output come up in our console tab. That console tab shows the confidence interval that we had in the PowerPoint slide. But if you are ever curious about what a function is in R, you can also use the help menu. And if I press or type question mark prop.test and run that line, there it goes, it will pull up some information in that help tab in the files, plots, and packages pane. So this will explain what does the prop.test function do and what arguments are allowed for that function. So notice this has more information than what I actually typed, and some of that is just default. So previously, when we were doing hypothesis tests, we instead wrote 58, 120, and then p equals a certain value. And I don't remember what it was exactly, so let's just say it was 60%. And then we get to decide, do we want to do a alternative? Do we want to do a right-tailed, two-tailed, or left-tailed test? So if I did a right-tailed test, it looked something like this. And we got this output where we are testing if the true proportion's greater than whatever that hypothesized value was. If we did a left-tailed test, we would change that to less than. And if we wanted to do a two-tailed test, we did two-dot-sided. Now, if you did not include that argument at all, if I just had the 58, 120, and our hypothesized value, it defaults to a two-tailed test. So earlier, when I was running this prop.test function, notice I did not include what that hypothesized value was, and I didn't include a alternative direction. That's because those are defaulted into that argument. So the new parts of the confidence level and correct equals false are added in there, and I can actually take out the confidence level and still get this exact same thing because it defaults to a 95% confidence level. However, if I wanted to do a 99% confidence interval, I would need to specify that for R because it does default to a 95. A 99% confidence interval will produce different estimates for that proportion, and a 90% confidence interval would also produce different estimates. So if you need to change that confidence level, just make sure that you're typing it as a decimal. All right, let's go back to example 3 that we were about to do. Here we have NC State's Student Life Office wants to know how popular Netflix is among students so they can decide whether to host a Netflix night event. They randomly surveyed 200 students, and 126 students report they currently have an active Netflix subscription. The office wonders if this is really different from a long-standing estimate that 60% of students subscribe to Netflix. So we construct a 95% confidence interval for the true proportion. Now the hypotheses, if we were doing a hypothesis test, would state that we have a null hypothesis equal to 60% and an alternative that it's just not 60%. This would create a two-tailed test. To create a confidence interval in R, we first need to check our conditions. And that first condition was randomness. We did collect a random sample of students, so that condition is met. For independence, each observation needs to be independent of each other. We are sampling these students without replacement, so we would check that 10% condition. The sample size was 200. That should be less than 10% of the student body if we assume enrollment to be more than 2,000 students. That would be the case for NC State, so we meet the independence condition. Lastly, we're looking at the normality condition. For this, we're checking to see if we have at least 10 successes and at least 10 failures. That would mean 200 times 0.60 for the hypothesized proportion gives me 120 successes and 80 failures. Both of these are at least 10, so our condition is met. When we run this in R, we are specifying prop.test with 126 and then 200. That's 126 successes out of the 200 sample size. So 126 students did have an active Netflix account. We are doing a 95% confidence interval, and we are turning off the continuity correction. This gives me an interval from 0.56 to 0.69. So we would interpret that to say we're 95% confident the true proportion of NC State students who subscribe to Netflix is between 56.1% and 69.4%. I don't know why that's out of order, but that's okay. All right, so can we connect the hypothesis test and the confidence interval in R? We can, but we do need to set the null hypothesized parameter. We would need to align the confidence level and the significance level, and then make the alternative hypothesis two-sided. So when we looked back at these hypotheses, we have a null hypothesis that's equal to 60%, and the alternative tells me we'll be doing a two-sided test. We can put that into R and do prop.test with, we had 126 out of 200. So we have 126, 200. Our null parameter was 60%. Our alternative hypothesis is two-sided. I don't have to type that argument because that is a default there. Our confidence level is 95%. And we're going to do correct equals false. When we run that, we end up with a confidence interval that we got before, and we can focus on the p-value. That p-value that we got would tell me to fail to reject the null hypothesis. That would mean that we do not have evidence that the true proportion is different from 60%. In fact, when we look at that confidence interval, it does capture 60% as one of the plausible values. So I have no reason to believe that the true proportion would be something different than 60%. But what if it had been a left-tailed or a right-tailed test? In order to do this, we would need to do the prop.test function twice. Once so that we can run this for the hypothesis test, because that would specify the left-tailed or the right-tailed part, and then again for the confidence interval. The hypothesis test will get me my p-value, a correct p-value for the left tail or right tail, and the confidence interval will work for a two-tailed test to give me the upper and lower bound of that confidence interval. Let me show what happens when we don't do that. So previously, we had a hypothesis, and let's say it is greater. I can run that command, and it would say a p-value for a right-tailed test. But notice the confidence interval. It goes 0.5699 all the way to 1. That's not the correct interval, and that's because this is not doing a two-tailed test. Now, a confidence interval is based off of a two-tailed test. So if I did less than instead and did a left-tailed test, I then have a confidence interval that goes all the way from 0 to 0.686. But if we change that to two-dot-sided, we get the correct confidence interval with a lower bound of 0.559 and an upper bound of 0.696. And those are slightly different. Notice that I didn't turn off the continuity correction. This is a one sample proportion test with a continuity correction. That's not going to matter too much. It did change slightly, but for a confidence interval, we should be doing correct equals false, and those numbers changed slightly. All right, the last section here is about a type 1 and type 2 error. We did talk about this in Math 152, but let's review that for a moment. So when we are making a decision about a hypothesis test, we are competing an assumption of what is true versus what reality is. So in reality, the null hypothesis is either true or false, but our decision is only using our evidence to either reject or fail to reject the null hypothesis. Errors do happen when our decision just does not match up with reality. A type 1 error occurs if a test rejects the null when the null really is true. That is, that the test finds convincing evidence for the alternative, but that alternative is not really true. The type 2 errors happen when we fail to reject the null hypothesis, but the alternative is true. That would mean that we do not find convincing evidence for the alternative, but in reality, the alternative really is true. We can think of this like a courtroom, and in a court case, we either decide if a person is guilty or not guilty. We don't really decide if the person is innocent, but we do assume that a person is innocent until proven guilty. So if the null hypothesis was true and I reject the null hypothesis, then we are convicting an innocent person. We have made a type 1 error. We have come to the wrong conclusion. It's based off of what evidence is presented in that court case. So if the court case tells me that I need to convict the person, they've made the error based off the evidence. We would not know that unless we find out in reality that the null hypothesis really was true. Alternatively, we make a type 2 error when we fail to reject the null hypothesis, but the alternative was actually true. So which one of these is the best choice for a given significance test? Well, that's going to depend on whether a type 1 error or a type 2 error is more serious. I guess this is backwards. My apologies. But so we typically look at the three significance levels of 5%, 1%, and 10%. And if we were basing that off of what we need for the hypothesis test, sometimes it's specified for us, sometimes it's not. We would justify that off for which one is more serious, a type 1 error or a type 2 error. A type 1 error, the probability of making a type 1 error is equal to our significance level. So if we know that a type 1 error is serious, you would want a very small probability of making a type 1 error, so you would lower your significance level. If a type 2 error is more serious, then you might be okay with a higher significance level instead. We can decrease the probability of making a type 1 error by using a smaller significance level, but there is a trade-off between the type 1 errors and the type 2 errors. As one increases, the other decreases. So if we make it more difficult to reject the null hypothesis by decreasing our significance level, we increase the probability that we will not find convincing evidence for the alternative when it is true. In this last scenario here, hospital administrators want to monitor whether recent staffing changes have affected patient wait times. Historically, the average door-to-provider time at the ER has been 45 minutes. After increasing the number of nurse practitioners, they take a random sample of 25 recent patients and find the average wait time is 47.8 minutes with a standard deviation of 5.6. So we're running a hypothesis test that the null hypothesis says there's no change in the average wait time, and the alternative is that it has changed somehow. This is a two-tailed test. The significance level is 5%, and we calculate a p-value of 0.019. This would tell me to reject the null hypothesis. So it would say, I don't think the true average is 45 minutes anymore. I have some evidence that the true average is not 45 minutes anymore. If an error was made, this would be a type 1 error. This is happening when we reject the null, but in reality the null would be true. So what would that mean in context here? This would say that the administrators found evidence that the door-to-provider times at this ER is different from 45 minutes, but in reality, it really is still 45 minutes. The last few slides here are just to check your understanding for these. So if you want to pause and work through these, you can check your understanding and I'll go through the answers with you. So in this one, if the p-value is 0.032, we should reject the null hypothesis, and so the correct answer would be B. For the second one, if we're interpreting this confidence interval, the correct answer is C. We are 95% confident that the true population mean is between 52 and 60. If a null hypothesized value lies inside the confidence interval, then that would tell me that I would have failed to reject the null hypothesis because it is one of the hypothesized values. Sorry, it is one of the plausible values. The hypothesized value would be inside the confidence interval, being one of the plausible values. The next one, we're just justifying which one is true. If we have rejected the null hypothesis and later we find out that the null hypothesis really is true, then we've made a type 1 error. In this one, we're focused on why is this an incorrect statement. Oftentimes people have trouble talking about what a p-value really does mean. A p-value is a probability value, and it's focused on the likelihood of seeing the sample result that we got. So in this, that p-value is not the probability that the null hypothesis is true, but it is a probability. It just happens to be a probability that we would observe the results that we saw or some more extreme results when we assume the null to be true. In this last one, we're looking at two researchers that are debating between two different significance levels. A 10% significance level versus a 1% significance level does have some trade-offs. Lowering a significance level reduces the chance of a type 1 error, but it does increase the chance of a type 2 error. So it depends on which one would be worse for a given scenario. a significance level of 10% might be okay in early exploratory research when we're trying to avoid a type 2 error making a false negative, because missing a true effect would be costly. But a significance level of 1% would be better in a high stakes context, something like where we're trying to get a drug approved, where a false positive is very dangerous. All right, so in the next couple of lessons, to finish out the rest of this unit, we're going to go into experimental design and talk about some differences between experiments and observational studies. We'll look at different types of experiments and some sampling methods, and then move on to hypothesis tests with two samples.